All right, so let's maybe say a few words about the problems. So the first problem was, as I was suggesting at the very end of the lecture earlier, that we can think about our update rule for how we update the quantum state conditioned on a measurement as the quantum generalization of what we know as Bayes' rule or Bayes' theorem in classical statistics. So in Bayes' theorem, we can say, you know, what, given some prior probability distribution, how do we update the state conditioned on that? And Bayes' rule tells us how to do that in terms of what's called the likelihood function, and then just renormalizing things, right? And that's quite similar to what we see here. I don't want to really, I know everyone's tired and so I don't want to waste time here, you know, going through all details. So I'm happy to highlight anything that you want me to highlight or discuss anything that you have questions on. So the first problem was really there to sort of show you how the quantum Bayes rule is similar, or in fact, equivalent, 100% equivalent to what's going on in Bayes' rule. So maybe we should cut to the chase. How does this quantum measurement differ from classical's Bayes' rule? Does anybody have any thought about that? Is the answer nothing?
So we had a small discussion already about that. And we came to the conclusion that the only difference is the uncertainty principle.
Absolutely. So, I mean, the difference between, so what is different in the classical versus quantum, in this case, the distribution, the probability distribution in X in this particular measurement scheme with that particular wave function is exactly what you would get from Bayes' rule. So the degree to which, you know, you squeeze your uncertainty, you would do that classically as well. The more you learn about the position, the less you are uncertain, and you would reduce it more and more. What is true quantum mechanically is that you cannot do that without simultaneously increasing the uncertainty in the conjugate variable. And that's because the quantum measurement will guarantee you to disturb the conjugate variable, in this case, the momentum. So really, the signature of quantum squeezing wouldn't just be a reduction of the noise, it would be an increase in the noise in the conjugate variable. That would be the signature that you really were doing squeezing in a quantum way. Okay, let's talk about the next problem, which is probably where people were at and is perhaps the most interesting of these three problems.
So I had a small question. I heard of these back action evading measurements, but aren't...
Yeah, that's a kind of, you know, the term QND, quantum nominal division back action evading measurement, is a kind of, it's a kind of historic kind of denotation or a historic language that people used. And the point is that often a measurement of position was done in some sense by seeing a time of flight and measuring its momentum. And doing so will disturb the position. So a typical measurement is a position disturbs the position. This kind of measurement of the sort that I describe here is a QND measurement, a quantum non-demolition measurement. It is a back action evading measurement in the sense that if the system had been in an eigenstated position, it will stay in an eigenstated position. And this measurement will not induce back action on the position. And so we call such a measurement back action evading. Of course, it can't completely evade the back action because the back action goes into the conjugate variable. And so this is an example of what we would call a quantum non-demolition measurement or a QND measurement, which is a back action evading measurement. But it's a kind of stupid term in my view, because no, you can't avoid back action. It's just that the back action goes into the thing you're not interested in. That's how you get away with it. Okay, so it's just a semantic term, which is confusing.
Okay.
Very good. All right, let's talk about this other problem, because I think this is a lot of fun. And it really hits an important point home. So in this problem, we're looking at it, the so-called damped harmonic oscillator. So this is the master equation that describes the damping of the harmonic oscillator. It has the Lindblad form with jump operators that are proportional to the annihilation operator, A. And this is the quantum mechanical description that describes the, for example, also if you thought about your harmonic oscillator as the mode of an electromagnetic cavity where there was one mode and photons can leak out of the mirror at rate gamma, then the jump operator corresponds to looking at the photons that leak out of the mirror. Okay, so what we're told here is the following. Let's suppose we start our mode of our oscillator, or our motion of the particle in a harmonic well, in a coherent state. A coherent state is a state that is not an eigenstate of the Hamiltonian. It doesn't have a definite number of energy excitations, or equivalently, it doesn't have a definite number of photons. It has an uncertainty number of photons, and that state is a superposition of photons of this sort. But it's very special, as you may know, in that it is an eigenstate of the annihilation operator. So if you act the annihilation operator on this, you get the same state back with the eigenvalue alpha. And that is true when you have this distribution of n, Fock states in your state, okay? So from the point of view of a harmonic oscillator motion, this corresponds to a wave packet that is oscillating, a Gaussian wave packet that's oscillating in the well. It's not a stationary state, which is, you know, one of the eigenstates of the Hamiltonian. It's a superposition of energy eigenstates, which corresponds to an oscillator going back and forth. From the point of view of photons, it's a state that corresponds to the oscillator of the electric field undergoing some up and down oscillation with some amplitude and some phase. Okay, now what you're told here is that if I start the system in this pure state and I let it evolve according to this master equation, it does not evolve into a mixed state. It stays a pure state. In fact, it stays a coherent state. It's just that the amplitude of the coherent state undergoes the classical motion. It oscillates in the well and it damps, but the state is always a coherent state, just with and ultimately it will decay all the way to the ground state. When T goes to infinity, this decays to 0, and that's the ground state of the harmonic oscillator, also known as the vacuum, if you were to think about this in terms of photons. Okay, so that's the given. All right, so now we want to think about this from the point of view of what we discussed today of quantum trajectories. And we know that the quantum trajectories involve a probability of jump and a probability of no jump. And we put them all together and we should get the evolution produced by the master equation if we ensemble average over all possible trajectories with the right weighting of the statistics. Okay, right. So the first question, so let's say we start in this state and then a jump happens, which corresponds to we detect a photon that leaked out of the cavity. And I ask you, what is the post-measurement state? Maybe I'm going to switch to the solutions now. And at the same time, let's see if I can find the damn thing. Excuse me. I just had this a moment ago. Let's see, open recent. Here they are. And I will share the screen. Okay. So before I show the solutions, what do you guys think? When a jump happens, what is the state of the oscillator conditioned on that measurement? It's confusing because we know the rule. The rule says we should apply the Krauss operator that corresponds to that measurement outcome and then renormalize the state. Now, the Krauss operator corresponding to the jump is the jump operator, modulo, factors. So let's look at that. Okay, so here's the state at the initial time, and then we want to know what is the output state conditioned on that measurement. So this is the rule, right? We apply the jump operator to the state and then we normalize. The jump operator is just this. We apply that to the state. And since this is an eigenvector of the annihilation operator, we just get the eigenvalue back. And the magnitude of that is just that. So when I normalize it, I just get the coherent state again with some overall phase that I don't care about because that doesn't affect the density operator. What? What the heck does that mean? That means that a photon leaked out of the cavity and we counted it, but it didn't change the state at all. How is that even possible? Does anybody have any thought about that?
Is that just like replenishing?
Yeah, so, it's an interesting point here. Let's go back to this expression. Okay, notice this state has a probability amplitude. If it's actually a coherent state, it has some probability amplitude to have an infinite number of photons, right? Because this sum goes from 0 to infinity. And so it's a probability of no photons, a probability of 1 photon, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to infinity, weighted by this distribution. Now, of course, as some of you may know, if you look at the square of this distribution, it's a Poisson distribution. The probability of having n photons is a Poisson distribution. And the Poisson statistics are exactly those that if you take away one thing from it, it looks exactly the same you would just get the same Poisson statistics once you renormalized it. So the replenishing is because there were an infinite number of photons to begin with. Subtracting one from the photon does not change the photon statistics at all. There's still exactly the same probability of having 0, 1, 2, 3, 4. If I annihilate one photon from this distribution, it has the same statistics. That is unique to the Poisson statistics. And the coherent state has those statistics. So even though we've annihilated the photon from the state, we haven't changed the statistics at all. And thus we in no way update the state. The state, our state assignment is the same, because after we've annihilated one photon from this coherent state, we have afterwards exactly the same statistics. Interesting. Okay, well, if that's true, how in the world does this thing decay? Because we know that what we just said here was that, you know, in the master equation, the solution is it becomes a coherent state, which ultimately over time will decay to the vacuum, which means at some point there's no, you know, there's less photons in the cavity, which on average than before, because the mean number of photons in the cavity is just the square of the amplitude of the coherent state. And the amplitude is decaying. So how does this happen from the point of view of the quantum trajectory? Well, shockingly, that happens because we don't see photons. Because if we look at the evolution under the no jump condition, we evolve according to the non-Hermitian effective Hamiltonian. And that evolution, if you go through and plug that in, gives me, because this is the number operator up here, the amplitude decays with exactly what we'd expect from the classical evolution. In fact, once we renormalize this, the output state is the decayed harmonic oscillator. It is the coherent state with that, but that evolution is occurring when we don't see photons. What are we talking about here? Well, the point here is that not seeing a photon is information. It's the information that actually in this system, there's more likely to have had amplitude in the vacuum than to have amplitude with photons. Because if I didn't see a photon, I just say, you know what? Actually, maybe there are no photons to begin with, because there's some chance there were no photons. As we see, this coherent state has some probability of having no photons. And the more we don't see it, the more we should say, you know what? Maybe it was the vacuum all along. And we keep renormalizing it. And over time, the longer we don't see the photon, at the end, there was no photon. And so a quantum trajectory in this case would be interesting. In fact, it would be deterministic. So if I were to look at this, say the absolute value of the amplitude as a function of time, when I don't see a jump, it decays. If I see a jump, I don't do anything. Then if I don't see a jump, it decays. If I see a jump, I didn't change my assignment. And so this ring down of the cavity will happen the same for every trajectory. In this case, every trajectory is the same and deterministic. There's nothing stochastic about it. And so when I look at the average over all trajectories, the state remains pure at all times. And that's what's going on in this problem. It's crazy, but true. I love this problem. It's just really just hits home the idea of how important, and in fact, the no jump condition is, you know, some of you may know about the use of oscillators of microwave cavities for quantum computing. So you may know about the famous experiments out of the Yale group from Michel Devereux and Rob Schlokoff and others, where they're using Schrodinger-Katz states and certain other states of the cavity that they manipulate with their superconducting qubit as a way of encoding quantum information. And it's exactly this problem. Photons can leak out of the cavity, but they don't do anything. They just deterministically can pump up the coherent states because it's decaying. The jumps would do nothing if I had a coherent state. When you have a Katz state, you have a superposition of coherent states. That's a different story. But this kind of quantum trajectories is essential now for people thinking about ways of correcting quantum errors that happen in quantum error correcting code. So it's pretty cool. Does anybody have a question, discussion about this?
Wouldn't alpha like be constant when we see a photon? So it would actually do something?
So when right when I see a photon, which is this click, alpha doesn't change. But in between the time that we don't see a click, then we renormalize the state more and more towards the vacuum and it decays. But at that instant, nothing happens. Unlike what we saw in the lecture, where this would jump down to 0 and you would project the system in the ground state.
Oh, okay.
Yeah. So there's nothing stochastic happening there. This is just a dotted line to say, hey, a jump happened here, but who cares? Nothing changed. The statistics are exactly the same. It's fascinating, I think. All right. It's late, and the next problem is somewhat technical. I just maybe will I want to go back to the questions and just explain what the questions is. It was part of something that didn't really come up in lecture very much, but I want to just mention it because it's an important, yeah. Okay, let us continue. Right. So, you know, one of the things maybe, I don't think this was perhaps discussed in Daniel Ladar's lecture, but is this important point that a mixed state has a kind of ambiguity associated with it. So we can think about a mixed state as a statistical mixture of pure states. And as we saw in today's lecture, we discussed that when you are in an open quantum system, you generally will go from a pure state to a mixed state, and you'll prepare a mixture which you can think about as the environment having measured the system, but not told us the result. And so each of these psi sub i's could be considered to be one of the prepared state produced by some measurement, and we weight that by the probability that that measurement occurred. However, that's not unique. In fact, as we discussed at the end of the lecture today, we could have done a different measurement. The different measurement would correspond to preparing a different ensemble. And it's another way of saying that the Krauss operators or the jump operators that correspond to the map are not unique. And they can be related to one another through this theorem. And this problem is just to show it. And I think it's just worth just looking at the solutions to see how it goes, to work it out. It's a bunch of mathematics at the moment, but it's an important fact, which is that you can prepare different statistical mixtures of pure states. And from the point of view of the observer, the measurement outcomes that you would see would be the same. That is to say, they would happen with the same statistics. And this is not always widely known that, and I want to emphasize, these are not the eigenvectors and eigenvalues of the density matrix. That is unique. There is only one set, well, up to the phase of the diagonalization of the matrix. So these psi's and phi's need not be orthonormal sets. If they were, then this would be the density, this would be the eigenvectors. So this is really more about what goes on when you make this preparation through the measurement model. The post-measurement states are not orthogonal. Does anybody want to discuss this further? Want me to show anything more about it? I think this is best done. Just look at the solutions. Is there something in the chat? Okay. Would you like me to show the solutions? I can do that. You're gonna get them yourself. Right. So question is, what is the relation to the maximally entangled states? So the states that are prepared in the measurement are prepared by whatever kind of entanglement exists between the system and the ancilla or the environment. They're definitely not necessarily maximally entangled, but it really has to do with the fact that what we described in lecture today was that the ensemble that we prepare depended upon the measurement we did on the ancilla or the environment. So for example, if we did photon counting, we prepared one ensemble of trajectories. If we do homodyne detection, we get a different ensemble. But the statistical mixture of those two different ensembles is the same. And what that problem is there to show you is what's the mathematical relationship between those ensembles. I think it's tedious to go through it, but I think you guys should just look at it yourselves when you feel like it. Before we break, does anybody have any other questions that you didn't get a chance to ask during the lectures or about the homework?
Hello, can you hear me?
Yes, I can.
Yeah, so I have sometimes I confused when I hear about the stochastic the idea. So can you explain it, please?
I'm sorry, I didn't hear you. So what? Can you repeat the question?
Yeah, I'm saying that when I heard about a stochastic, so I will confuse sometimes. So can you clear this idea? What does stochastic mean?
What does stochastic mean?
Yeah,
I see. Oh, it's just another word for random. So if something is stochastic, it's not deterministic. So I'm sorry I didn't define that term. So when we talk
that means,
about,
can you say noise as a stochastic?
Noise?
Can
Yes.
I say noise as a stochastic?
Yes. So noise, what we call noise is an evolution that has a random variable that we don't know, right? So if I would look at a signal that's a noisy signal, we would say that it evolves stochastically. Stochastic just means randomly. It's just another name for random. You know, English is weird. It just has many words that mean the same thing. They're only a slight nuanced difference. So in a quantum trajectory, the evolution of this wave function is stochastic because the measurement outcome is random. And so depending on the measurement outcome, we update the state differently. In the case that we looked at in the lecture, either we see a photon or we don't see a photon. If we see a photon, a jump occurs, and that's one kind of evolution that occurs on the state. If we don't see a jump, we have a different evolution that we apply to the state. And because we have to flip a coin to decide or roll the dice that gives us the right statistics, the evolution of the state vector is stochastic. Now, what's interesting is that when I look at the the statistical mixture of all the density matrices, that becomes deterministic. So we have unraveled the time evolution in terms of a statistical mixture of stochastically evolving states. Does that make sense? Or at least do the words make sense?
Yes, yes, it's making sense.
Yeah. Does anybody else have any last things they want to discuss?
I'll just throw a monkey wrench into that last statement.
Yeah.
You say that it becomes deterministic if you average all the density matrices, but there are many, but this can be for systems that are inherently quantum mechanical and have no classical analog. That's kind of weird.
It is. Well, so what it's saying is the following. The Schrodinger equation, as you know, is deterministic, right? And there is nothing random about the Schrodinger equation. The only randomness comes in is when we observe and we see a measurement outcome, right? And then there is a random outcome. The master equation corresponds to the evolution of the state in contact with an environment when we don't observe the environment. That evolution is deterministic because we're not doing any measurement. But what we have seen today is that we can understand that deterministic evolution of having lost coherence as there's information there, but we just didn't capture it. And interestingly, we can simulate this deterministic evolution as a statistical mixture of random evolutions. So it's a probabilistic, yeah, there's just a lot of different pieces to wrap your brain around on this, but it's a lot of fun. I have a question. What if the environment size is comparable to the system? Well, that's an interesting question. So, you know, as I mentioned in one part of the lecture, there was some hidden assumptions going on about the nature of the open quantum system having to do with the Markov approximation. And the Markov approximation is saying something about the size of the environment, meaning that the number of degrees of freedom in the environment must be approaching something that is uncountably infinite if we are to ignore any memory effects. If the environment is not a real environment, does not have sufficient complexity, then information is not lost, in which case it can come back into the system, and it's not really an open quantum system in the same way that I'm describing it. So all of the ideas and techniques that we discussed today really are only applicable in the Markov approximation, where the environment is effectively infinite.
Hi, can you hear me?
Yes.
Yeah, so I wonder, like, what's the final result of the first problem and like the interpretation?
Right. So the first problem, what we see in the first problem is that in both cases, you have exactly the same update. You start with a Gaussian. It's exactly like I showed in the PowerPoint, where we have the Gaussian distribution, we did the measurement, and we end up with a squeezing of the uncertainty and a random center. That happens both classically and quantumly. But so there's no difference. That the difference in the quantum is actually in the back action on the conjugate variable. So in a classical setting, we can in principle imagine a measurement that is sufficiently good that only measures the position without in any way affecting the momentum. But in the quantum mechanical setting, if we measure the position, we must disturb the momentum. And thus, that's where the difference comes in. It comes into the conjugate variable. You can see that in the solutions that will be posted.
Okay, thank you. So to see like the change in momentum, we like basically use the wave function, and then we have like the del x, and then like calculate that again. Okay,
that's correct.
All right, thank you.
All right, one. So we have one more question. Can we observe the apparatus pointer state in the superposition of here and there? In principle, we can try to cook that up, right? So I think this was perhaps the question that was asked at the very beginning of the lectures earlier, which is the how shall I say this? So what we have discussed is the measurement model paradigm. We have the system, the ancilla, and the observer, okay? And the back action that we get onto the system depends upon the measurement that we do on the ancilla. Now, the question is, what if the pointer states were well separated, right? They're not overlapping. Is there a measurement I could do that can not project this onto one or the other, but into the superposition here plus there, as it's said in the chat? And the answer is, in principle, yes. I would do a measurement with one outcome that would be here plus there, And the other outcome is here minus there. Those two states are orthogonal. And in principle, I could cook up a measurement with those two outcomes. And if I got here plus there, I would project the system into the symmetric superposition. And if I got here minus there, I would project the system into the negative superposition. So in principle, such a measurement is doable. And those kind of measurements have been thought about in the context of what's known as a quantum eraser. So in a quantum eraser, you are erasing the entanglement that you have between the system and the environment in such a way that you preserve the coherence. So it's a very good question and something that people do think about and have done. All right, everyone, it's been a long day. Anyway, I hope you guys had some fun too. I certainly do. And I look forward to hearing more from everybody. You're welcome to contact me with questions, further questions, and more discussions. So have a good rest of your day, everyone. And thank you, Richard, and all the helpers today. Bye-bye.
Bye.